Welcome students. In the previous video we have seen the design of stem and we have arrived at the dimension d is equal to 243.5 and we provided 450 and a tapering stem, that is this tapering of 200 mm at the top and 450 mm at the below portion. Now let us provide the reinforcement there. So, for the reinforcement calculation, this is the formula used, which is there in IS 456 2000 point clause number G 1.1 page number 96. MA is equal to 0.87 Fy ASTD into 1 minus AST Fy divided by BD FCK, where Fy is the grade of steel and FCK is the grade of concrete, B is the width, D is the depth. So, AST has to be computed. So, from the formula after substituting we arrive at 1007 mm square. So, providing 16 mm diameter bar at 150 mm center to center spacing. So, as 16 mm diameter bar, a single AST will be pi by 4 into d square. So, 201.06. So, distribution steel of 0.12% of the cross section. So, cross section is nothing but of the portion is 0.0012 into 1000, taking B into D. So, depth is 0.45, maximum I have taken, and we get 540 mm square. So, providing 10 mm diameter bars at 250 mm center to center on both the faces. Now, let us see the stability calculation. So, first we have to find out the pressure distribution, because the next step is, as you can see in the diagram, we have designed the stem now. Now, we have to design the heel slab. For this, we need to know what is the pressure acting on it. So, pressure distribution has to be computed. Now, let us see here. So, stability calculation. So, pressure distribution is calculated by the forces acting and movements of all forces about the heel point. Now, what we have done is, we have given the notation. So, this portion I will be taking it as W1, the heel slab I will be taking as W2, and here there is a soil which will be acting as W3. So, all the weights, that is self weight of stem, self weight of base slab and the self weight of earth, will be acting downwards to the CG of the earth. So, let us start. So, stability calculation. So, I have made 4 columns, that is loads, forces, distance and the moment. So, load, let us see W1. Now, W1, what is W1? It is nothing but the stem portion. So, this is W1, which is 200 mm, height 4.78, this is 450 mm and this is inclined portion. So, what I have done, this I have divided into two parts, one as a rectangle. So, rectangle of dimension 200 by 4.78 and remaining 0.25 into a triangle. So, let us find out its self weight. So, first of the rectangular section. So, it will be 0.2 into 4.78 into density 24, density of concrete. So, let us see 0.2 into 4.78. So, this is 0.2 into 4.78, a rectangular portion which is 0.2 into 4.78 into 24. So, this is working out to be 22.944 and the distance is taken from the heel slab. So, its CG will act at half. So, it will be 0.1 plus 1.55. So, it is 0.1 plus 1.55, which is 1.65. Force into distance will give you moment. So, 22.944 into 1.65 is giving it as 37.857. Now, W1 again I have divided into a triangle also. So, this triangle dimension is, height is 4.78 and this distance is 0.25. So, area into distance. So, area is half base into it. So, half into 0.25 into 4.78 into density. So, this is the force and it is acting again from the heel slab. So, it is 1.55 plus this 0.2 plus 1/3 of 0.125. So, it is 1.55 plus 0.2 plus 1/3 of 0.25. So, it is 1.833, which is working out to be 26.285. So, this is the force multiplied by distance, this is moment. Now, let us see W2. Now, W2 is nothing but the base slab. W2 is nothing but the base slab. So, dimension of this base slab is rectangular, which is 0.45 into 3 into density. So, it is 0.3 into 0.45 into density, which is 432.4 and the width is half of half of 3. So half of 3 is 1.5 meter. So force into distance we got 48.6. Now W3, this is, so W1 is of stem, this is of base slab. Now W3 is of the soil. So let us see W3. So W3 is this portion whatever we have. So this has a dimension of, you can see, 1.55 by 4.78. So let us see. So 1.55 into 4.7, taking it as a rectangular portion into the density. Now this density is of earth, that is W is equal to 18, as in the given in the question. You can see density of earth 18, because in this portion you can see here there will be soil, so the density of soil has been multiplied. So it is 1.55 into 4.78 into 18, which is 133.36, and it will be nothing but whatever is there from the hill slab. So 1.55 divided by 2, so this multiplied by this we get 103.354. These are the moments, these are the forces. And one more thing, moment of earth pressure. So here you can see the earth pressure is also having a moment as well as from this side. So that is given by the formula K into WH cube by 6. So already K we know that 0.33 we have worked out, that is 1 minus sin phi divided by 1 plus sin phi into 18 into 4.78 cube divided by 6. So this is directly movement. So let us take a summation. So summation of all forces, this 203.044, summation of all moment, this 325.202. Now we have to find out the application. So let us see. Distance of point of application of resultant from the end A. So I will be finding out with respect to this. I have prepared a distribution table. So this is A point, this is B point, this is C point, and this is D point. I will show it in a diagram. Where are those A point, B point? So this is a A point, this is a B point, this is a C point, this is a D point. A is this edge of the hill, B is the base of the stem, C is also base of the stem, and D is the toe slab end, So this is what distribution I am marking it here. So this is nothing but A, B, C, D. Hope so you got. So this is 1.55 meter, this is 0.45, and this is 1 meter. Now we have to find out the pressure distribution. So let us find. So first find out the eccentricity. So distance of application of the point of resultant from end A. So it is from the end A from here. Okay, let us see. So which is given by Z is equal to summation of moment divided by summation of the forces. So summation of moment is nothing but 325.200, and summation of the forces is nothing but this. So this is working out to be 1.606 meters. So we got the resultant distance of area. So eccentricity is equal to E is equal to Z minus B by 2, where Z is nothing but the 1.601 which we have found out, and B by 2, where B is the width of the base slab. So the width of the base slab is working out to be 3 meters. So let us see. So substituting 3 by 2, so 1.101. Now let us see B by 6, width by 6. So 3 by 6 is 0.5. So what is happening here? Our E value is 0.101, and the constitution of B by 6 is 0.5. So obviously this is less. So E is less than B by 6. So 0.101 is less than 0.5. Hence it is eccentricity is less than the B by 6. Now let us compute the minimum and maximum pressure. So minimum and maximum pressure at the base are given by sigma x sigma summation of W divided by B into 1 plus or minus 6 E by B, where E is the eccentricity, B is the base of slab, okay. W is the summation of forces. So summation of forces we have computed it in the table, which is here you can see stability calculation force. Summation of force is 203.044. So this we will substitute it here. So it is 203.044 divided by 3 meter width, 1 plus or minus 6 into eccentricity we have computed it, which we have you can see here, which you have got it as 0.101, okay, divided by 3. Now if B by 6, if eccentricity is greater than B by 6, then we have to substitute B by 6 value. Now, one for plus and one for minus. So, if I compute this with plus, I will get sigma max. If I compute this with minus, I will get minimum. So, pressure maximum. So, substituting as plus, I got 81.375 kilonewton per meter square and a minimum 54 kilonewton per meter square. So, minimum will act here 54 kilonewton and maximum will act here 81.35 kilonewton. Now, this is the maximum stress. So, maximum stress is within the limit of the SBC, which is 200. So, it is less than 200. The pressure distribution is trapezoidal. So, this is a distribution table A, B, C and D. So, at A minimum will act, that is 54, at D it will act as 81.35. So, we have to find out at this point. This is a pressure distribution at the base. So, this is how the pressure distribution is to be calculated from the stability calculation. So, let us see the design of heel slab and design of toe slab in the next part. Thank you.